Hey what's up guys, my name is Cherno. Welcome back to the third episode of my ray tracing series. So, last time we spent pretty much the whole episode talking about math. I highly recommend that you take a look at that episode even if you're not interested in math, because the whole spirit of the series obviously is learning how to do absolutely everything and knowing how everything works. And I think for ray tracing specifically, like this is such a good opportunity to actually dive deep into how stuff works on paper, map it all out, understand it, and then translate that into like code and see images appear from nothing, which is just super cool. Now, what we're going to do here today is building on the math that we actually worked out on paper last episode. We're going to take the exact same like equations, put them into C++, and have them render a sphere for us. The really cool thing about today's episode is, again, it's going to be identical to the stuff that we did on paper last episode, but you're going to see it kind of applied, you know, per pixel to actually render an image. But to make that happen and also make this a little bit more like sustainable for the future as our code gets more and more complicated, I want to dive into the existing code that we've got and kind of restructure it a little bit so that we have basically this concept of a renderer. So over here inside our ray tracing project, let's go ahead and make a new file, and we're going to make two new files actually called renderer.h and renderer.cpp. Now, one of my goals with this series is to keep things as practical as possible. So I don't want to spend like too much time talking about like the architecture of a renderer or anything like that. Like this is not really the purpose of this series. We don't have a namespace, do we? I wanted a name for this, but I don't think we have one at the moment. So let's just go ahead and write the class without a namespace. So what I mean is like, I don't really want to put too much emphasis on like how to design a renderer, you know, for a ray tracer or for a real-time application or whatever. We're going to just keep things as simple as possible. And so the purpose of this really is it's going to be a class which holds some context, but the idea is the input is a scene description. So we have like some form of description of like the 3D world that we're trying to render. And then the output is an image which holds the pixels that the renderer has produced, which describe that scene. So fundamentally, that is like the purpose of this class and this whole kind of architecture. Now, at the moment, we really don't have a scene. In fact, if we run the current state of our application, it is this. We just have a bunch of random pixels, which basically just proves that we have the ability to write to a Vulkan image and then display it using ImGUI every single frame. And that's what we're doing here, which will look much better like in real life and not in a YouTube video because of the compression. Now, because of that, we're not really going to have an input at the moment, but in the future, this will take in like a scene, which is going to basically be something that holds like the description of our scene, like meaning like all of the objects inside the scene, you know, stuff like a light environment and all of that stuff. But for now, we're just going to have a kind of empty constructor. Now, this constructor will have stuff in the future, but for now, I'm just going to keep it as just equals default, just so that it's there. Now, the real function of this renderer at the moment is going to be this render function, which literally is going to do all of the work. So the goal here is to basically render like every pixel that we have that makes up that viewport that you saw there, which currently has random pixels. Now, because of the way that this is going to work, the target of that render function is going to be an actual image. So I'm going to go ahead and include walnut image. And then we're going to, similarly how we like basically had this image here, right? I don't really want to have the image just inside walnut app.cpp. We're going to move this image to being inside this renderer class. Let's also include memory so that we can use shared pointers. And this is going to be a walnut image. Now, I'm deliberately like not, you know, putting this into the walnut namespace or using namespace walnut or anything like that. I don't want to do any of that because I want it to be clear like what stuff is from walnut and what stuff is our stuff that we're writing as part of this series. Now, going back though to our main kind of walnut app class, there are obviously a fair few things here that are really important for us to take with us. For example, before we render, we check to see what the viewport width and height actually is, because we want to be able to render an image that is the same size as our viewport. And if the viewport size has changed, which is what this function does over here, it will actually create a brand new image with that new width and height. So that's obviously important stuff that we need to make sure that we actually do inside this renderer class somewhere. I think what I'll do for now is I will just make like a on resize function, and this on resize function will just take in a width and height. Now internally, it's obviously going to know the current width and height because an image actually holds like a width and height. So we can kind of only do the resize if necessary, and to make things a little bit easier, inside this function where we'll basically do this, we can check to see if the, okay, well if there's no image, we'll have to create one anyway, but basically we can check to see if image get width obviously matches the width, and then if like the width hasn't changed, and if the height hasn't changed, then of course we don't need to resize the image. Now, I have actually added a new function into Walnut called resize. And what this will do, if we take a look at its implementation, you can see that it will check first of all to see if the image even needs resizing. So has the width and height, is the width and height different to what we already have? And if so, then it's going to release and then reallocate that memory. So this is like just a little bit easier to deal with than having to completely like delete the image and create a new one. One of the reasons why I really like this design as well is because the original kind of image handle, so to speak, so in other words, like this image, like its pointer doesn't change, the object doesn't change. So everything that used to hold a reference to image, like as a shared pointer, obviously still has that same image, because you're not deleting the object and making a new one, which obviously will have a different like spot in memory somewhere, right? You're actually keeping that same object and then changing like the insides basically, which is what we're doing here. We're releasing it like from our GPU memory and reallocating that GPU memory within this same kind of object. So I like that because it does keep things quite a bit cleaner. So ultimately we need to do this, but obviously if we don't have the image in the first place, then we're going to have to create it. And my plan, by the way, with this is we're going to call renderer on resize first. So when we actually render over here, what we're really going to do is call like renderer resize and then renderer render. So we're going to see if it needs resizing by just passing in the viewport width and height. And then we're going to call the render function, which will actually render into that image. But the only flaw here is that we do actually still need to create the image in the first place if it doesn't exist. So I think I might change this just because resizing will be the main case. If there is an image, then we can just call image resize like this, assuming that it needs to be resized. But again, because this does the check internally, I'm going to just call resize, and then obviously if it doesn't need to, it's not going to resize. It's not going to waste time reallocating memory. And then over here, if there is like no image in the first place, then we obviously need to create it with the width and the height, and then whatever format we want, which we'll keep as RGBA for now. Now we also obviously have like a CPU side buffer, which represents like the data of the actual image, and that buffer is called image data. So we need to also take that with us. So we're going to come over here and grab image data, and we're going to put it into here. And this is also something that obviously we'll need to get like initially created over here and then resized as well. So let's go ahead and delete it, and then we're going to basically just recreate it like this and set it equal to width times height. Now a few notes here. Obviously this actually doesn't need to be called if we're not resizing the image. So even though this does have that check, I'm going to add it again here, and we're not going to call it if it doesn't need to resize. But basically if image get width equals width and image get height equals height, so in other words, if the image is already the right width and height, if it's the correct width and height, then we'll just return if there is an image as well. So if there's no image, it will still create a new one, obviously, because there is no image in the first place. However, if there is an existing image, it will exit out of this function if there's no resize necessary. So we'll just say no resize necessary. Otherwise, it will resize the image, then jump over here, delete the image data, and then recreate that image data as well. Now, if image data is null, as it will be for the first time, that's fine. This will do nothing, and that's perfectly okay. Whenever there's like a delete null pointer going on, I always feel the need to explain it, because some people still don't understand that it's totally valid to do that, and you don't need to do stuff like if image data delete it or anything like that, because the delete operator will actually free, which it will eventually call, that does that check for you. Okay, so we now have an image. So render, I might actually drop this down just because that's the order that they're going to get called in. So let's go ahead and basically move our image generation code that we have at the moment into that renderer class to make sure that everything's working as we expect. So we can delete the image from here and in fact replace it with just a renderer. I'm going to go up here and obviously include our renderer class that we just created. That will already be obviously instantiated with the default constructor. The only thing we need to do is in render, we need to call renderer resize, as that comment says, with the width and the height. And then we just need to call renderer render. And that is it. So none of this needs to be done. This is our new like rendering code that I'm going to take and put into the render function. So that's what we're dealing with here. Let's go ahead and grab the image width and the image height, and then random. Let's come over here, grab the random class. We don't need that there anymore, and we'll just include it over here. This is going to be walnut random. So that's our image data, and then obviously to actually set that into the Vulkan texture, we also need to call image set data, which we will do after we've gone through and set that CPU side buffer, filled it with our random pixels. Yeah, and then we can keep last render time. Okay, so this stuff now becomes basically if renderer get final image, as we'll call it. So let's go back to the renderer. I'm actually going to call this final image and not image. The reason being that it's possible that we're probably going to have more than one image in like our kind of render pass pipeline, because we might do like some post-processing. So for that reason, I'm just going to call it final image, just so that it's clear that this image, just make sure that we've renamed it everywhere, because this image is in fact like kind of our final buffer after the rendering's complete. That's like the final resulting image that we want to probably take and then display. So let's go ahead and write a function called getFinalImage, and then that will return final image. Back in Walnut app, if final image is a thing, in fact, I might just call this auto image equals getFinalImage. Really should, I don't know, this stuff's new. This like showing me what the types are. I don't know where that, and it did not tell it to pop up, but it's popping up now. So I don't know, maybe I'll disable it, although I guess it might be useful. I don't know. Let me know what you guys think, like for videos. Is this useful to like know the parameters or whatever? I don't generally like it too much when I'm programming. Okay, so render is undefined for some reason. This I think is size, so I think we're just missing a curly bracket, and that's probably why. Okay, cool. So that is looking pretty good. I think that's it. So just to summarize, what we've just done is some very light refactoring. We've just moved all of our renderer related things into a renderer class that will also kind of act as like the thing that will accept our scene and will output a final image that we can then just take and display in our viewport. So if we hit F5, hopefully we'll get the same result, or a compile error. So I somehow got rid of that. I don't know. Things got weird when we started refactoring that part. Okay, cool. So we've got the same result, obviously, and everything is fantastic. Okay, so now that we've done that, let's dive back into the renderer class and take a little bit of a look at how to kind of architect this part of it a little bit better. So if you've done any kind of GPU programming, like using Vulkan, OpenGL, DirectX, anything like that, you're probably familiar with the concept of pixel shaders or fragment shaders. And these are basically just GPU programs that will run for every pixel of whatever you're trying to render. So when triangles get rasterized, every pixel that is generated as a result of that rasterization process will invoke like an instance of this pixel shader, and a shader is just a name for a GPU program. So what I want to do with this code is I actually want to structure it to be a little bit more like that. So in other words, I want us to effectively be able to write like a pixel shader over here in C++. Another great example of this is ShaderToy. So ShaderToy is a website where you can basically write like a pixel shader and you will get the result rendering over here in real time. So you can see that we have like a pixel shader over here. This is kind of the format that we write it in. So you can see that we've got, it looks like a single function. It doesn't have like a for loop in it or anything. However, this exact code gets invoked for every pixel of this viewport that we're rendering here. And an important feature of this is you can see we have like a UV coordinate. Now in this case, the UV coordinate, if we just output the UV coordinate alone, let's add in a Z value of like 0, then this is what the UV coordinate will look like. So we've simplified it a bit. Let's get rid of all the extra stuff. This is as simple as it is really. What this is showing us is a value between 0 and 1 across the x-axis, which is being displayed as the red channel, and then from 0 to 1 along the y-axis, which is being displayed as the green channel. That's why you see it get greener as you get higher up, because that value goes from 0 to 1, and 1 is full green, 255 in an RGBA buffer, or I should say in like a 1 byte per channel kind of integer format. And then obviously with the x-axis, it gets more red as you go kind of in the positive x direction, because again, it goes from 0 all the way to 1. And in the top right corner where we have 1 on the x and 1 on the y, we see yellow because that's the combination of the red and green channel on full blast, and then no blue because we put in 0 for blue, and then alpha is 1. This specific setup over here is going to be really, really useful to us, and it's going to simplify a lot of things. So I want to basically be able to write this exact program as it appears here, in the format it appears here, which means no for loop, nothing like that, but inside our C++ code. So let's make that happen. So what I'm going to do is write a function. I'm going to just make it private for now. We'll call it per pixel, just so it's clear. And it's going to return a uint32t, which is going to be our resulting color. Now it's going to take in a glm vec2, which is going to be our coordinate. So what this is going to be is essentially the frag coordinate that you see here. Now it's going to be a little bit different because it's actually already going to be in this format, but basically what frag coord is as an input is it's just like the pixel coordinate in pixel space. In other words, this would be like the resolution is 1200 by 675, and so we would have a coordinate like in that range, like the middle would be like 600. That's why you're seeing this kind of division here, where it's dividing frag coord, which is in pixel space, by the resolution, which of course is 1200 by 675, to map it into like a 0 to 1 range. So that is already going to be the input here. It's going to be already in that 0 to 1 range. In fact, we're actually going to change it a bit later on to be in a -1 to 1 range, because that is even more useful. So let's go ahead and implement this function. Now, as you can imagine, what we need to do now is simply call this function from like within a for loop like this. So that kind of is our goal. But from here, we actually need to work out this coordinate. So to make things a little bit easier to understand, I'm actually going to convert this to be a nested for loop, where we're going to iterate through the y, which of course is going to be like the outer for loop that's going to be the height of our image here. And then the inner for loop is going to be x. Now the reason why we write y on the outside here is because we want to be more friendly with the CPU cache, essentially. So the reason why this is important is because if you think about the way that the buffer is laid out in memory, as we go like one uint32t forwards, we're going to essentially be going horizontally across the image. If we had flipped this, then it would be a bit weird because we'd be skipping a bunch of memory by basically going like a full row forwards. And that's going to actually slow down our program because the CPU is not going to be able to fetch that memory as easily. But anyway, once we have this kind of nested for loop where we have like the x and y, we can easily work out what the coordinate should be. So our coordinate is just really going to be whatever x is divided by that total width of the image. So we can divide it here. And then the same thing for our y coordinate as well, of course, but with height. Now there's a fatal flaw in this, and that is the fact that these are both integers. And so when we do an integer division here, it's really only going to be 0, like for all of these. So we need to make sure that we cast at least one of them like this to a float, and then it will do a proper floating point division. Just for completeness sake though, I like to do both of them, although just one is necessary. Okay, so we now have a coordinate that we can pass into per pixel, and then the result here is going to be image data. That color that per pixel returns, we're going to store inside the image data buffer at the appropriate location, which, speaking of like what is the appropriate location, because we don't have that I variable anymore, well, we can easily convert this kind of two-dimensional coordinate x and y back into that one-dimensional offset of that buffer by just doing x plus y times whatever the width is. Because what this is doing is just multiplying like the y coordinate by like how big each row like supposedly is, and then just adding in that like x column offset. So now it's the responsibility of per pixel to actually provide some kind of color. And just to do something extremely easy, let's just set this to be magenta. So we're going to have a nice pink color here, and I'm actually going to come over here and also include GLM because we need that since we're referencing vec2 over here. So let's go ahead and hit F5, and hopefully we'll see that pink viewport, and there it is. Now, since we did just convert our whole program to be very much like Shader Toy, why don't we try this exact example? So UV is already there, that's our coordinate, so really we should just be able to set frag color to vec4 UV 0 and 1, right? Now, we're using integers for now as like our colors. So it's going to be a little bit different. We'll have to actually convert into that. But ultimately, we're going to switch to using floating point images eventually. I'm almost tempted to just do it now. I think we'll do it next time though, just so that we can keep things like it was originally. But to make this happen, ultimately what we would need to do is just simply grab like the red channel, which we'll set equal to coord.x. If we just multiply that with 255 and then cast that to be like a byte like that, then that will give us our red channel, and our green channel will be coord.y. And then we need to basically shove this into here. So let's go ahead and make something like that. And then we'll OR in G shifted left 16, or actually 8, and then red over here. So that I think should be correct. No, it's black. Oh, whoops, I forgot to add in more zeros. Okay, there we go. So you can see we get the same result. It's actually flipped upside down though. So you can see that that kind of black area is over here and the yellow area is over here. Now the reason for that is actually to do with how IMGUI displays our image. So if we go back to here, what I'm actually going to do is add one more parameter here, which was originally optional, and that is the UV0 and UV1 parameters. And what I'm going to do is basically set, maybe I'll just drop this down so it's more visible. I'm going to set the UV0 to be 0, 1 instead of 0, 0, and the UV1 to be 1, 0 instead of 1, 1. So basically what I've done is I've just reversed the UV coordinate of the Y axis here. So that V of the UV has now just been inverted basically, and that will flip our image. Now there's a bunch of different ways that you could flip this image, to be honest. You could change so many things, but this is just the easiest way to do it. And that's what I usually do. Okay, so if we run this again, now you can see we have a result which perfectly matches what we actually see here. And we also should be able to resize it. That's something I didn't actually check. And you can see that that also obviously works and gives us kind of our expected range of colors here. So that is really, really important stuff, because this kind of coordinate system that I've just shown you here, and also this function here, which we can use to render things per pixel, this is going to form the basis of how we actually decide where to shoot out our rays, like from the camera, to see if they intersect with our sphere, which is what we're about to do. So now things are pretty simple. We have the coordinates, and we're able to run some calculations for every single pixel which makes up our viewport. So this is now where the math comes back in. So this is the math that we did in the last episode. As a quick recap, what we know is that the equation of a circle is over here. Here it is. The equation of like a ray is this thing over here. And we can basically substitute this into this to do all of this math and more or less get like this final equation before we actually substituted some real values to see if we could actually get our array to intersect with our circle. So if you haven't watched that math episode, then definitely watch it. I'll have it linked up there. But also, if this kind of math interests you and if you want to learn more, then I can't recommend anything better than the sponsor of this video and this ray tracing series, Brilliant. So Brilliant is an amazing website with lots of different courses on various STEM topics, and their math courses are literally the best I've found so far on the internet. And the reason for that is because they're extremely engaging, interactive, and practical. They don't just throw information at you, have you watch videos, do all that stuff. They actually give you like interactive controls to play with so you can visually understand how stuff works, which I think is so important for the kind of math that we're doing. I mean, we're literally using math to create a ray tracer. Like, we're using math to create images. Like, that is like the most visual thing ever. And to be honest, like pretty much all math is like that. It's just that a lot of platforms and a lot of different courses out there, they don't fully take advantage of this fact. And me being like a very visual learner, I just think that that's by far the best way to learn. They've got lots of different math courses which cover pretty much every inch of what we're going to be doing in this ray tracing series. And these are all just really high quality courses. These calculus courses, for example, benefit so much from this kind of visual interaction. Brilliant also have plenty of courses on other STEM topics. So if you're interested in like computer science, data structures, just general science as well, and the applications of that, lots of stuff there to check out. And speaking of checking it out, you can get started for free by just going to my link in the description below. But Brilliant have also been nice enough to offer the first 200 of my subscribers 20% off an annual membership. All you have to do is go to the link in the description below and sign up. So go ahead, check them out, see if there are any courses you're interested in. Huge thank you as always to Brilliant for sponsoring this video. Okay, so once you have brillianted up and you've also gone back and watched that previous episode of the ray tracing series and you understand all of this, it's finally time to take these weird equations and put them into C++. So where do we even begin with that? Well, okay, let's kind of break this down because there are a few differences between the equations and what we're actually doing here. First of all, I did mention that we, of course, did the math in 2D, whereas over here with our ray tracing, we're going to be obviously doing this in 3D. Now the difference is so small, again, that it really doesn't matter. We just add in that extra Z axis, the Z dimension. So what we need to do here is fairly simple. We need to take this equation, this bx squared plus by squared t squared plus 2ax, this equation over here, and then just substitute the values the same way we did here with actual like variables. And then we can use this quadratic formula to solve this equation, just like we did on paper, but we can obviously just do this like in C++. So the first thing I'm going to do is just write out this equation as like a comment over here, just so that it's clear what we're doing. The only thing that we actually already substituted here was this -4, which if you remember was the radius squared. So I'm going to leave the radius squared alone. And we have this, which as you can see is exactly the same equation as we had on paper. Now there is one thing we can do to simplify it very, very slightly, and that is the fact that you can see that there's a 2 at the front of both of these terms. So what we can actually do is remove it from there and just kind of take it out like this. We'll just do this here to simplify the actual C++ code a little bit. So now that we have this, remember t is what we're solving for. That is going to be the distance along that ray. We have all of these unknown variables. Now the only real unknown variables we have are a and b and r. That's it. So what is a? A is going to be our ray origin, which going back to our math, we know that from that ray equation, a plus bt is what we kind of define these variables as. A would in fact be the origin of the ray and B would be the direction of the ray. So A is the ray origin, B is the ray direction, R is the radius of the sphere or circle, doesn't really matter though, and T is like the hit distance, we'll call it. So now all we have to do is fill these in. So let's go ahead and do that. Now I'm going to name these variables a, b, and c just like they appear in the quadratic equation. So if we go back to the quadratic equation and specifically like the quadratic formula, we have this kind of a, b, and c inside the quadratic formula. And a, b, and c obviously they map to the actual values, the actual coefficients of the different parts of this quadratic equation. So the coefficient of t squared is a, the coefficient of t is b, and then finally that constant term here is our c term. So that's why I'm going to name these a, b, and c. So in other words, this is going to be a, this is going to be b, and then this is going to be c. So what is a? A is bx squared plus by squared. Now what you see here is just x and y. There's no z because we were doing this in terms of a circle. But that's how you add z. It's just an extra term there. Like wherever we had x, you can see that we obviously split everything up by x and y, right? We have x and then we have y. We have x and then we have y. We have x and then we have y. Well, z is just like an additional term there. So what that means is that what this is going to be here, it's going to basically be the ray direction, like squared, so multiplied with itself, and then all like summed up together. So the first question we have then is if we really do want to figure this out, like what on earth is going to be that ray direction? And this is where we're going to talk about how we shoot rays out from the ray origin in the first place. Now, because I wanted this episode to be kind of not too long, we'll say, I'm not going to spend a huge amount of time talking about how to shoot rays out. All I'm going to tell you is that if we have our camera over here, we can say that this is just at like 0, 0, 0, doesn't really matter. Then all we have to do to calculate a ray per pixel is effectively just use this coordinate that we have. But remember, it's a bit weird because the current way that the coordinate is set up, it goes from 0, 0 to 1, 1, which is a little bit weird if you consider that to be like your direction. If this is our camera here and we're looking kind of along the same axis that it's looking at, it means we'd kind of shoot all of our rays this way and nothing would kind of go around, right? So what we can do is remap these coordinates to be from -1 to 1, rather than being from 0 to 1. And we can do that really, really easily. When we figure out this coordinate, what we can do is just multiply the coordinate by 2 and subtract 1. And of course, that will just remap it from being from 0 to 1 to being from -1 to 1. And that will kind of make sure that 0 is kind of down the middle and all these other rays kind of go out along like different sides. Now, for a lot of reasons, this is not really the final solution that we'll stick with, but it's a really easy way to just get started and it will totally work. We could normalize that as well if we wanted to make sure that they're all the same length, because obviously at the moment they won't be. So what that means for us here is that this coordinate really is our ray direction. So let's get started implementing this equation. So it's going to be coordinate x squared plus coordinate y squared plus coordinate z squared, because we are in 3D space. But wait, you say, that's a vec2. So how do we deal with this? So if we go back to what we drew here, what we're kind of looking at here, I mean, this is a 2D image, so of course it's easy to just deal with two kind of dimensions, two axes. But if we picture this being like the actual coordinate of each pixel on the viewport, if we were to like obviously rotate this onto its side, so this kind of whole thing, this plane gets rotated 90 degrees onto its side, it would just look like that. So these rays all at the moment kind of just, they have no depth to them, obviously. What we want to do is we want to kind of shoot them that way. So the camera's facing a particular direction, and we want to shoot the rays that way. So apart from being all across this area, we want them to actually have depth so that, if we do rotate them, if we rotate this view like this, we actually see them have depth like that. So the way that we can do that very easily is just by adding a Z coordinate, adding a Z axis to our ray, and then setting it to 1 or -1, depending on which way we define our forward to be. Now for this example, it's actually not going to matter if it's +1 or -1, not going to matter at all. We're going to just use -1 for now, just because that's if you're used to OpenGL, that's a very kind of common way of thinking about your forward direction. And really this comes down to whether you're dealing with a right-handed coordinate system or a left-handed coordinate system. But again, for now, we're not going to care about any of that. What we're going to say is that our three-dimensional ray direction is going to be coordinate.x, coordinate.y, and -1. So there's that -1 on the Z, and then obviously these are going to also be between -1 and 1. And then if we want that to be a unit vector, we can normalize it. Now, this is not going to matter for now either, so we'll leave that off for now just so that you can see the result. Okay, so now we're obviously going to change this to be our ray direction. Now this is looking pretty big, and if you've been paying attention to your vector math, you may have noticed that what we've written out here is just the dot product of ray direction with itself. So we're squaring each term and then summing them all up to get a nice float. So we can rewrite this as just being GLM dot ray direction and ray direction, just like that. And that's it. That's the same thing. And you can see over here, we're also going to have another dot product, but this time with the ray origin, but we'll get to that eventually. So this is our A term now. That's it. It's just ray direction dot ray direction. That's the kind of A coefficient of our quadratic equation. Now let's move on to this kind of B coefficient. So what's this going to be? So float B is going to be 2 times AX BX. So what is this? This is the ray origin X times the ray direction X plus the ray origin Y times the ray direction Y. And then obviously it's going to be the same for Z. So this is also a dot product because we're multiplying each component of A with each component of B and then summing them all up. So this is just going to be the dot of whatever A is, which is our ray origin, which we haven't really defined. So let's define that. Again, I'm just going to make it 0 as I did in my diagram. It's just going to be ray origin dot ray direction. And that's it. That's our B. So simple. And then C is going to be this last part over here, which is going to be the ray origin dot itself, but then we're going to subtract the radius squared. So let's go ahead and define a radius for our sphere. I'll just set it to 0.5, so we basically have a 1 unit diameter sphere, and then we should be able to sort this out. So this is going to be GLM dot the ray origin with itself, and then we're going to subtract the radius squared. So we'll just do radius times radius. That is our entire quadratic equation written out here, ready to be plugged in to the quadratic formula so that it can actually be solved. So what we'll do today is we'll just focus on the discriminant, which remember should be enough to see if we actually intersect the sphere or not. It will tell us if there are any solutions. So that part is b squared minus 4ac. So let me just write this out. B squared minus 4ac. So let's go ahead and calculate it here. Discriminant. So b squared is obviously going to be b times b minus 4 times a times c. That's our discriminant. And so guess what? Based off of this, we can now check to see if it's greater than 0, then there are solutions. If it's greater than or equal to 0, there's at least one solution. And then if it's less than 0, there are no solutions. So we can now use this to return a color based on what the discriminant is, right? So in other words, if the discriminant is greater than or equal to 0, then we can return, let's say, that magenta color. Otherwise, we can return just black, I guess. So black will be our background, and then if we hit the sphere, we should see that magenta color. And that is it. Let's see what that looks like. Okay, so we just get a solid pink viewport, right? Which tells us that we're hitting the sphere. I mean, I kind of maybe would have expected to see a sphere in the middle. I'm not sure why I would have expected that, just I would have, right? But if you think about it, this actually makes perfect sense. Because where is our ray origin? 0. Where is our sphere origin? 0. So what's actually happening is we're shooting rays out from here, And then we have this sphere that's here. So we're basically inside the sphere. And as we hit this, of course we're hitting it, this entire sphere fills our viewport. So what we need to do to see the kind of image that we were maybe expecting, which I don't know about you guys, but I was expecting to see something like this with the sphere in the middle, we need to obviously move this sphere. We need to translate it back along the negative axis, the negative Z axis, back in 3D space so that it doesn't fill our camera's viewport. Alternatively, we could of course just move the camera back. So let's go ahead and try that. Let's keep the X and Y of the camera at 0, but let's move this back maybe like 2 meters or something like that. And -2 of course would be moving it forward, just like in the direction of our ray. So let's go ahead and set this to +2 because that will be kind of moving it back. Remember, forward is -Z. And look at that. We have a sphere. We have ray traced a sphere. Amazing. Hopefully, this has shown you guys just how cool this kind of practical application of math really is. Because again, we've gone from literally like having this stuff on paper, right, to being able to write it out programmatically per pixel and actually draw this image. And this is just the beginning, because remember, what we did on paper then later is we actually solved the quadratic formula to work out the exact location of the hit along the sphere. Because at the moment, it kind of looks like it could just be a circle. It's not. We've obviously used that kind of Z dimension as well. This is actually all being calculated in 3D space. This is in 3D. It's just it's flatly lit, so we can't tell. So what I want you guys to do for homework is go in and see if you can solve the rest of the quadratic formula. Then you'll get the actual like ray hit distances. See if you can work out the 3D coordinate of everything and maybe even figure out like the normal of the sphere. And for bonus points, see if you can apply some shading to it to see that it is in fact in 3D. Now, this way of doing things has like a bunch of flaws, obviously. And like one of them is if we resize this viewport, you can see that it gets stretched. Why? Because obviously there's no concept of like aspect ratio or anything. We're still in that 0 to 1 space, both horizontally and vertically. And by 0 to 1, I mean -1 to 1. So clearly we need to account for like the width of our viewport or the aspect ratio of our viewport to kind of not send rays out. So that could be another little homework assignment for you. But yeah, this is the beginning. This is the beginning of being able to ray trace an image. So let's go ahead and clean it up a little bit. I'll get rid of this stuff. I did say I would show you the kind of ray direction normalization, but you're not going to be able to tell the difference here. It's going to look exactly the same, as you can see. So it's not really necessary. It's just something that mathematically to me seems like it should be. But for this specific thing, it's not going to be necessary. When we start getting into actually solving the quadratic formula, then obviously the direction and the actual length of that directional vector is going to determine these t values and all that stuff. So it is a good idea to normalize it potentially for some things if you need accurate hit distances, but you know, for just drawing this kind of part of it, it's absolutely fine. So yeah, that's the final code. It'll be up on the GitHub page. So feel free to download it and run it on your computer and play around with it. Another thing you could do as well, by the way, is you can see that the equation of a circle actually has this kind of A and B, which is the origin of the circle or origin of the sphere. So see if you can maybe move the sphere around. We can obviously move the camera around. That's just the ray origin. But of course, it would also be like useful to be able to move the sphere around. So see if you can work that part into the equation as well. But other than that, that's it. That's the beginning of our ray tracing journey. We finally actually used ray tracing to draw something on the screen. So very, very exciting stuff. Hope you guys enjoyed this video. If you did, please don't forget to hit the like button. Next time, we're basically going to actually solve the quadratic formula and see what we can do with that information and add some shading so that we can actually like see the form of our sphere, and we'll move on from there. Thank you guys for watching. Don't forget to check out Brilliant using my link in the description below, and I will see you guys next time. Goodbye.